advisors, in particular Professor Park, for invitation to this wonderful workshop. I really enjoy very much the talks and conversations and food. Okay, today I want to talk about surface superconductivity and the relation to surface Smectic liquid crystals. And this is one of my favorite topic, and probably is a little bit too old. And then I will go to some new stuff, anisotropic schematics. But this part is not very complete. Okay, let me start with surface superconductivity. And actually, many people already mentioned during this conference that superconductors and liquid crystals are very similar. Okay, and probably I should skip such kind of introduction, but I do want to mention that from a mathematical point of view, superconductivity is interesting because this is kind of property depending on the topology and geometry of the sample. This is not only the physical property of the material. Instead, this is the property of the sample, depends on the shape, depends on geometry. And also, you observe a lot of concentration behaviors like boundary layers, like vortices, and like Peter mentioned during his first talk, the surface has important effect on liquid crystal, but this is same to superconductors. Okay, and I will emphasize on the analogies between superconductivity and liquid crystal. So let me quickly start with the Ginsberg-Landau functional. Comparing with liquid crystals, the function for superconductivity is too simple, at least to people in this room. For superconductivity, we have we have autoparameter, which is complex value function. We have A, which is a real vector field. So psi tell you how much superconductivity you will expect, and A is kind of induced magnetic field. So we do have two parameters, lambda and kappa, and probably in some mathematical journals you will see only parameter kappa, and most of the time people let lambda equals 1. And this H is applied magnetic field. So here I'm interested in the effect of applied magnetic field onto the superconductivity. Okay, and maybe I also need to emphasize that the first term is gauging invariant. So we will go to this kind of functional later. Let me explain again the notation. Grading sub A psi means grading psi minus I, A psi. So this is the vector field. And grading A square psi means the second order operator. Okay. Okay. And when we talk about superconductivity, we mean that psi is not 0. And in the case when psi equals 0, you lose superconductivity and the sample is in normal state. Okay. Okay. All right. Let me just skip a lot of notations, and the Lagrange equations not needed right now. Okay. So for a magnetic effect, when you place a sample in the applied magnetic field, and when the applied magnetic field is very, very strong, then the sample is in the normal state. Normal means you lose superconductivity. Okay, so this is the kind of usual material. And then you reduce the applied magnetic field until you reach some critical field Hc3, and then you see that, roughly speaking, superconductivity will appear somewhere on the surface. Okay, and this case, when people say that you have superconductivity nucleation. And when the applied field is a little bit below Hc3, then you have surface superconducting state. It means that the whole surface is in the superconducting state, but the interior is still in the normal state. And then you reduce the applied field further to Hc2, then you see some nucleation of superconductivity inside the sample. Okay, probably you expect to see optical soft lattice when applied field is close to Hc2. Okay, of course this is a big open question in mathematics, how to verify this. Okay, then when the applied field between Hc1 and Hc2 is kind of vortex state, and the superconductivity is strong inside, but still you observe some positions where magnetic field penetrates the sample and you lose superconductivity there. Okay, and when you even lower the applied magnetic field, until the applied field below Hc1, then the sample is in the so-called massless state. So everything is perfect superconducting, no vortex. Okay. Now this is a rough description of what will happen when you place applied magnetic field when you place the superconductors in the applied magnetic field. Here I want to mention that the first guy who predict surface superconductivity was Saint-Jean and Jean, and they actually do mathematical analysis, and they say that if you have a sample which occupy half space or half plane, and if the applied field is perpendicular to the plane but parallel to the boundary, then you observe some kind of superconductivity on the boundary. And they have a critical field Hc3 over Hc2 is approximately 1 over 0.59. Okay. This is the first work tell people that you have such kind of phenomena. Right. And then I want to consider if you have bounded sample. Okay. If you have bounded sample, if you have applied magnetic field, what is Hc3? And what will happen when the applied magnetic field reach Hc3? So I do some rescaling, and to make life easy, let lambda equals 1. And this is applied field, which is proportional to a fixed constant magnetic field. So sigma is parameter, h is a fixed unit vector. Okay. Then you do again rescaling, let a equals sigma a, another a, and you write down your functional in this form. Instead of kappa a, you have kappa sigma a. Okay, and then this is corresponding to the applied field h times sigma here. Okay, so mathematically you can easily define Hc3. It is the smallest sigma such that the normal state lose stability. The normal state is no longer global minimizer. Okay. In other words, the trivial solution became not global minimizer. So this is the mathematical definition of Hc3. Okay. If you go to a physical book, they have different kind of definition of Hc3. They measure what will happen when you see the first vortex. But mathematically, I guess this definition is easier to handle. Okay, and then we can compute the value of Hc3. Let's start with two-dimensional case. When we talk about two-dimensional, actually we mean a cylinder. A cylinder of infinite height with constant cross-section, and you have applied magnetic field parallel to the axis of cylinder. Okay, then you reduce everything to two-dimension. Okay. On the two-dimensional, you can also define Hc3 similarly. Okay, and then we have that in two-dimensional case, Hc3 equals kappa of beta 0 plus, okay, now we have plus a constant C1 over some 3/2 power of beta 0 times kappa max plus higher order term if kappa is large. Okay, and what is beta 0? Beta 0 is the first eigenvalue of magnetic shooting operator in the half space with magnetic field, unit magnetic field. And so this is beta 0. And C1 is determined by beta 0. And kappa max means the maximum value of curvature of the boundary, because now we reduce to two-dimensional. So for two-dimensional domain, you have a boundary which is a curve. For this curve, you compute the curvature. And kappa max is the maximum value of the curvature. Okay. So this is the value of HC3 in two-dimensional case. And from this formula, you can guess, because C1 is positive, you have positive sign. When the apparent magnetic field is very close to HC3, where you can observe the location where superconductivity first appear. It should appear near the place kappa max. The curvature is close to kappa max. The maximum points of the curvature of boundary. Okay. Okay. So this result tells us the geometry do play roles in this phenomenon. Okay. And maybe I mentioned here again that when you consider nucleation of vortices, it should appear, in two-dimensional case, it appears where the curvature is smallest, just opposite to this formula. There are a lot of further discussions. Here I want to mention Fournet and Eiffel. Eiffel is in Paris 11, and Fournet is in Denmark. They use their powerful semi-classical analysis, micro-local analysis. They get much better and better estimates of everything. Okay. And then you may want to ask, what will happen if you reduce the apparent field further? And we just mentioned that physicists believe you should have surface superconductivity. Okay, so this is the results. If you reduce the apparent magnetic field, but above HC2, we believe HC2 is something like kappa, although we cannot prove. Above HC2 and far below HC3, okay, then what will happen? We first observe that all the parameters will exponentially decay away from boundary. So inside the domain, you see almost nothing, no superconductivity. But on the boundary, you have uniform concentration of all the parameters. Actually, the energy concentrate almost uniformly on the boundary. So the energy or any subdomain D is proportional to area of length of the intersection of the partial omega and D. Okay, so if D is inside domain, the intersection is empty, so leading term is 0. If the D is touch the boundary, so you measure the part of the boundary of D on the surface. Okay, so this is actually tells us energy distribute uniformly everywhere. Okay, and we wish to have something better. We wish that the order parameter will uniformly converge to such kind of function. So inside domain is converged to 0, outside is converged to a constant C, everywhere same C. Okay, and Almog and Eiffel can show a weak version. They said in the sense of integral, this is true, but in the sense of pointwise limit, they don't know. So it's still open. Okay, now let me go to 3-dimension. And in 3-dimension, the situation is much more complicated. Actually, we will have such kind of function P of x. Here, let me denote by kappa 1 and kappa 2 the principal curvature of the surface, and let me denote by theta sub H, the angle between applied field H and the principal direction corresponding to kappa 1. Okay, an angle between applied field and one principal direction. And then we can define the function P of x, and it depends on geometry, kappa 1, kappa 2, depend on angle between applied magnetic field and the geometry. Okay, so depend on both the geometry and applied field. Actually, the relation between applied field and the geometry. And then we take the minimum. Okay, I just remind you, in 2 dimensions, we have maximum. In 3 dimensions, we have minimum. Take a minimum of this function P over the boundary where applied field is tangential to the boundary. Okay, this partial omega sub H is not the whole boundary. It's a part of boundary where H is tangential to surface. Okay, and then we have the following conclusion. AC3 is, okay, the first leading term is same, kappa over beta 0. Now we have minus sign. Okay, in 2 dimensions we have plus. Now we have minus. And now we take a minimum value over the part of boundary where applied field is tangential to surface. Okay, 2 dimensions we have plus, we have max. 3 dimensions we have minus, we have minimum. Okay, and also we have this factor kappa to power 1/3. So when kappa is large, this term is very large, and the whole thing is much smaller than kappa over beta 0. So in 2 dimensions we expect AC2 is kind of kappa, but in 3 dimensions it's much smaller than kappa. Okay. And then you ask what happens when applied magnetic field is reduced from AC3, and we see that superconductivity nucleates first at the subsets of the boundary where the applied field is tangential to the surface. Okay, so imagine you have an ellipsoid. Applied field is in the z direction. So then partial omega sub H is the equator. Okay, so we prove that superconductivity nucleates at the equator. Okay, and then it expands over whole surface and into boundary. And actually, FA can do better, and after this he can show that actually nucleate first in some position on the equator where the P of x is the minimum. Okay. And later on they have much better estimates, and they are still improving the results. Okay. And here I want to mention many names, many works, but I don't think I should give name one by one. But I want to mention that Joe and Park. Okay, it is a little funny to me that experimental observations of surface superconductivity has been done very recently, and to me, to my knowledge, I know the first observation is 2003 by a group in Israel. They can observe surface superconductivity in some single crystal. Okay. And later on, they have a lot of observations. And probably here I want to mention one question by a physicist from Israel. He said that when he measured AC3 over some single crystal, okay, and he observed that he measured that the ratio between AC, okay, when applied magnetic field perpendicular to the face of a crystal, and according to Dejean's theory, according to this Schindler, he said that Dejean's theory should predict the ratio equals 1, but they measure is the ratio is bigger than 1. They measure is 1.28, and they said that this phenomena cannot be explained by Dejean's theory. So they believe this is a very big progress. And then when I receive their preprint, I'll tell them that actually when you measure HC3 over the crystal, you cannot only measure one face, actually you should treat it as the bounded domain, and you have several faces. Maybe they are appropriate perpendicular to one face, but it's not perpendicular to another face. So, so what I try to say is De Jong theory is still correct, no any contradiction, because you need to consider other faces. Okay. Now let me go to liquid crystal part. Okay. Skip this introduction part. Here I want to use the energy introduced by De Jong and later on by Lubinsky and Chen. So the energy consists of two parts. The first part is, okay, basically for order parameter psi, which corresponds to Smectic, and the second part is Olsen flank. Again, it's too simple to you, but still too complicated to me. Okay, so you look at the first term, you have two coefficients, C parallel and C perpendicular, just like Dr. Zhu mentioned yesterday. But in his model, he has more terms, higher order terms. And here I only have two terms. And in case C parallel and C perpendicular are equal, then you have grading sub Qn psi, grading psi minus IQn, very similar to Ginsburg lambda. But if C parallel and C perpendicular are not the same, it's different. And like Dr. Zhu mentioned, C perpendicular could be negative. Okay, and for nematic part, I just use the usual Olsen flank. Okay, and now what's the meaning of psi square? This is a kind of intensity of symmetric layering, okay? And n now corresponding to the directorial field of the symmetric. Okay, and later I will talk about the parallel part of grading sub Qn psi and perpendicular part. So let me mention again. Parallel part means this way. So parallel to n. Okay. So projected to n, and perpendicular part is the minus the original grading minus the parallel part. Okay. 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 Let me skip this part. You already see a lot of introductions, and many people have been working here. Let me mention again some people among the audience, in particular Professor Park and Dr. Zhu, and of course Professor Zhang Bo and Ming-Chun Hong and many other people also working on flow, working on many partial regularities. Let me just skip this part. Okay. De Jong observes the similarity between superconductivity and liquid crystals. And he said that many effects which occur in the Ginsburg lambda system should have their counterpart in Smectic A. Okay. I guess this is a part of the work he won the Nobel Prize. Okay, he said that when you look at the superconductivity, you have a normal state, and you know that magnetic superconductivity repair magnetic field, and you have umbilical soft lattice. When you look at the liquid crystal, you have Smectic, and this is the genius part of De Jong. He sees that Smectic is kind of counterpart of superconductors because both of them have letter S, and nematic should be counterpart of normal state because they have both n starting with n. However, to me it's hard to imagine why liquid crystal repair twisted and bound, and this is what he mentioned and what he said that important in his work. And so later on people believe that umbilical soft lattice should have counterpart which is twisted green boundary. And another similarity between superconductors and the liquid crystal is people found new phase not from laboratory. Instead, they found by using mathematics. Okay. People found by using mathematics the type 2 superconductors first by computing and then observed in laboratory 10 years later. And people found a twisted green boundary in mathematical analysis, and 1 year later in the experiments. Okay, now my question was how to verify the de Jong theory. Okay, of course, a lot of people have already verified, but I want to verify it in my way. In particular, I want to ask, what is the counterpart of surface superconductivity? Okay, so I guess if we compare two energies, if you look at the leading term, in superconductivity you have nabla kappa A per psi. In liquid crystal, you have nabla Qn per psi. So this term should place role in the comparison of analogy. Okay. So here I give the definition of QC3, very similar to HC3. Okay. QC3 is the first number of Q where the trivial solution loses global minimality. Okay. So mathematically, you can easily write down this definition and QC3. And you want to tell people?
So what is a trivial minimizer?
Has only trivial minimizer means psi equals 0, and m is the nematic. Okay, you go back to this energy when psi equals 0. If you have global minimizer psi n when psi equals 0, and this is global minimizer, and this is trivial, and it turned out that n must be the minimizer of this part, the nematic. Okay. So for superconductivity, you know that when applied magnetic field, when you place applied magnetic field, you have critical value AC3. Okay, then you observe surface superconducting state, and for liquid crystal, when you change the wave number Q until it reaches critical value QC3, you should observe surface Smectic state. Okay, so at least sounds similar because 3 letters S. Okay, so we may form this kind of triple S conjecture that surface Smectic state exists, and which is an analogy of surface superconducting state. And I should ask Professor Doi and your opinion whether this is the reasonable conjecture or not. Okay, maybe we will go with this. Okay, the answer is the following. We cannot give a full proof using full functional, but we prove in some sense for the simplified model, even simpler than what I wrote. So actually we prove that the functional E can be approximated by a reduced Ginzburg-Lambda functional. I will tell you what it is. And minimizers of reduced Ginzburg-Lambda functional do have such kind of property. Okay. So for some parameters, this approximation is true, then you do have such kind of surface Smectic state. Okay. So we can say that for parameters in the region, so that the approximation is valid, the surface Smectic states exist. Okay. And here I want to mention that Armoga also get some results similarly independently. Okay. Maybe I should skip the details and go tell you what is the reduced Ginzburg-Lambda functional. Actually, you fix n. Okay, in the original functional we have psi, we have n, and we use the Olsen Frank. Now you fix n, so drop the Olsen Frank. You only keep the first term. This is what we said, reduced Ginzburg-Lambda. Okay, and the variable is only psi. Now n is fixed, and now you fix n. You minimize this functional for psi in H1, and then you minimize n in the set of trivial minimizer. Okay, and trivial minimizer is given by rotation of some fixed vector field. So actually you can write the minimization in this way. So first they minimize psi in psi, the minimizing n in the set of trivial minimizer. Okay. And we show that if K2, K3 is large, K1 doesn't matter, then minimizers of original functional converge in H1 to minimize of the reduced functional. Okay. So this means if K2, K3 are large, K1 not vanish, then approximation is correct. Okay. Then you look at the how to describe the surface Smectic state. Actually, we want to say that the order parameter concentrate on the boundary. Okay. So we say that you fix n, which is the trivial minimizer. You look at the part of boundary where the angle between this n and the normal vector of your surface is smaller than half pi. Okay. And this means n is somehow close to tangential to the boundary. Okay. So this part, this set is the small portion of boundary where the small layer near the boundary where n is almost tangential to the surface. Okay. And then we can show that for some value of wave number q, the order parameter concentrate on this small region. Okay. Away from this small region, order parameter is very small. Okay, this is what we said. Order parameter concentrate in this small layer. Okay. And by this way, we say that the solution present the boundary layer behavior. Okay, so instead of giving the proof, let me give some explanation. The first one is when Q is close to some critical value, a stable parallel nematic state must be like this. Instead of saying that every trivial minimizer is stable, we say that some kind of trivial minimizer give us stable parallel nematic. Okay. Not every trivial minimizer is stable. And how to judge it? You look at the eigenvalue of some magnetic shooting operator. Okay. Okay, then if you let the wave number decrease and reach some critical value, and we observe symmetric nucleate inside the boundary layer where the n is tangential to the boundary. Okay, what is the n? N is a stable nematic. It is tangential to the boundary. Okay, and if Q is reduced further, symmetric layers expands along surface, and the interior remain in the nematic. Okay, very similar to surface superconducting state. Okay, very similar. So in this, so let me skip the proof. And now go to the third part. I just mentioned that in the Smectic part we have two parameters, C subparallel, C subperpendicular. Now I want to ask how the people always say that liquid crystal is kind of anisotropic material, and we want to ask how to describe anisotropy by using in terms of such kind of parameter. And in this part, we try to understand the anisotropy of liquid crystal by using the parameter C parallel and C perpendicular. So let the C parallel go to 0, C perpendicular go to 1. And you can do reverse part, C parallel to go to 1, C perpendicular to go to 0. So that similar. Okay. So let me write down C parallel to equals 1 minus epsilon square, where epsilon is very small. C perpendicular is epsilon square. Okay. And you let epsilon go to 0 and ask what happened. Okay. Okay. And of course, you know that the limiting functional is very degenerate because you lose part of the gradient. Okay. Okay. And actually, it is true that we need to understand this limiting functional to understand the behavior of minimizing sequence. Minimizers. Okay, of course, we assume omega is a bounded domain with pseudo boundary and giving boundary data for n, which is HC 1/2. And let me mention that because the degeneracy of our functional, you cannot expect. It's hard to expect that the limiting functional can have good minimizer in the usual Sobolev space. Instead, we introduce some kind of partial Sobolev space. Okay, what is it? It is the completion of C1 functions and the following norm. Here, instead of giving grading, we're giving partial part of the grading. The directional derivative in the direction of n. For example, if n is E1, the unit vector in x direction, this is just a partial psi, partial x. Okay, but now n could be varying, so n changes directions, but n is unit vector. N is a unit vector, so but it can change directions. Okay, in this kind of norm, you define the partial Sobolev space, and of course, this space can only enjoy partial properties of usual Sobolev space. Okay, and because the norm is defined, the space is defined by the closure of smooth function, so we ask whether the element in this Sobolev space has directional derivative, and we say yes in the weak sense, only in this direction along n. Okay, and because we have this partial n psi, we can define the parallel part of grading sub q n psi, and this is just the notation. We do not mean we have grading. Okay, defined by partial n psi minus iq psi times n. Okay, and if psi do have grading, this is the usual partial part of grading. And different to usual Sobolev space, this space is not continuously embedding in L4. But in our functional, we have L4 term for the order parameter. So we need another space. We use L4 PH1 parallel, which is completion of C1 and this norm. Instead of L2, we use L4. Okay, and then we can safely minimize our functional. But first part depend on n, so we do not use linear space. Instead, we use some kind of bundle. So n is from h1 omega s2, and for each n, you have this space. So attached to each n, you have linear space. N vary in this h1 space, and this give you. So each fiber is linear space, but the base space is not. Okay, how to say? So the whole thing is not a linear space, kind of bundle. And then we can show that if this functional f parallel q, the limiting functional, if it has a minimizer on this bundle, then you go back to the energy for liquid crystal when emission goes to 0. You have subsequence of minimizers which converge to one of minimizer of this limiting functional. And let me show you again the limiting functional. Okay. So original functional is like this. You have two terms, parallel part and perpendicular part. And this is defined in H1 Sobolev space. And when you take a limit, you drop this term, you only leave this parallel part. Okay, so this is the degenerate functional. Okay, and then if this limiting functional has a limit, has a minimizer, then we can show that the sequence of minimizers subconverge to a minimizer of the limiting functional. Okay, then you ask when this limiting functional has a minimizer. Let me show you one particular case. I just mentioned that we only have partial result. Let me define P psi 1 parallel. Okay, sorry for a lot of dirty notations. What is this? This means that the perpendicular part of this function equals 0, and the psi itself has unit modular. Okay. Roughly speaking, this means that the gradient part is parallel to n, and n psi itself has a modular 1. Okay. I will show you some examples how this set look like. Okay, suppose this set is not empty, then we can show that the limiting functional has a lot of minimizers. In fact, all these set, every element in this set is a minimizer of the limiting functional. Okay, and this set could be very, very large. And then in that case, the original minimizer of the liquid crystal converges to one of this functional. Okay. Okay. So this gives us case that we do have such kind of convergence. Okay. And however, in some usual examples, this set is very large. Okay. So you, first of all, you do not expect the minimizers have any compactness. We have so many minimizers for the limiting problem, and secondarily, you can only have subconvergence. Okay, so let me show you some examples of such kind of set. The simple case, when you have omega, which equals unit interval times d is two-dimensional. Okay, and n is E1, which is 1, 0, 0. So what is the parallel space? The partial Sobolev space is L2D H1. So this is actually equivalent to usual H1 space of one-dimensional, defined on interval. And then you take a L2 mapping from D onto this space. Okay, and the perpendicular part is defined on interval mapping to H1 space on D. Okay. I just show you that P parallel perpendicular 1, which is actually orthogonal to L2 space from D to S1. So this is infinite dimensional space. And the minimizers of the limiting functionals consist of L2 space. Okay, consists of infinite many dimensional space. And this also tells us that the partial Sobolev space do not have embedding into L4 because it has only L2. Okay. And let me show you a little bit complicated example. Consider unit ball with n equals x over normal x, the popular mapping. Okay. Okay. Then PH1 parallel is such kind of space L2 defined on S2 mapping into H1. Okay. And in this space we use the measure lambda r squared dr. Okay. And what is the space P psi 1, the set of minimizers is L2 from S2 to S1. Again, infinite dimensional space. Okay. Again, we have many, many minimizers. Okay. And maybe I should not mention this one and kind of complicated definition. Okay, if we have another n, which is e theta. Okay, e theta is rotation along the xy plane. Okay, minus x2, x1. Okay, then the space looks a little bit strange. Okay, so pH1 parallel is such kind of space. For any fixed r, you have H1 space. Then you integrate this H1 space, you get L2. And in this space, you assume some kind of periodic condition. You get this L2 star. Okay? And how to integrate the space? And this is the definition. So in each R, you have Sobolev space, and then you integrate. Okay. And the set, we are mentioned, the set of minimizers now looks strange. If Q equals 0, it's very large. Again, L2 space of kind of integral space. If Q is not 0, this set is empty. So we do not have any minimizer for our limiting functional. And in that case, situation will be much more complicated, and you expect kind of oscillation or kind of chaotic behavior for the minimizers of our liquid crystal. Okay. Okay. I want to take 1 minute to talk about another question. Okay, we just mentioned that you check the parameters C parallel, C perpendicular to study the anisotropic. But you can also study the anisotropic behavior by letting K1, K2, K3 be very different. For example, you let K2, K1 go to infinity, okay? And then actually you are leading to this problem. You minimize Q of n in this in some space. And here I must mention that Professor John Ball mentioned that space is kind of part of model, and I'm very happy to learn this. And if you define this minimizing problem in H1, more or less, most likely you should not have minimized. But if you define this space in the weaker space, here you only require Q of n is in L2, nothing on divergence. And then it's a different story. So our question is, if the infimum is positive, can it be achieved? If infimum is 0, again, this is a different story. Actually, this is related to Evans Giga problem, very famous problem, a lot of progress here. And for infimum positive, we only have one particular example. And when omega is two-dimensional disk, when boundary data make a constant angle with the boundary, then we know the minimizer exists. Minimizer is not in H1. And except this example, we only have other very trivial examples. And we don't know whether minimizers exist. And the computational results show that even in 2 dimensions, if you try to compute the minimizer of Q, and joined with Golowinsky and Linping, we found that even in 2-dimensional, you observe a lot of line singularities, many lines. Okay? And recently, joined with Moner, we tried to figure out some simple case, but still we have not get a good result. Okay. And related to this question is a joint work with my student Chen Jun, who is among the audience. Again, we need to minimize Q. Okay? And I include this part here because we observe several places minimizing Q, but I starting from some problem in liquid crystal. Okay? And in the classical bone field model, you have this kind of functional, and in the special case, when you let E equal 0, you only have B, which is Q of A. You are leading to minimizing this functional. Okay, some nonlinear function of square of Q of A. Okay, and when Q of A is very large, this functional is the order 1 growth. Okay, give you a lot of difficulties. And classical Brownian field model is not perfect because in the whole space, they do not have final energy solution. I mean, yes, they do, but all the final energy solutions are trivial. Okay, so several people try to figure out this imperfect. Okay, and actually, some people mentioned that probably because the Brownian field model is kind of perturbation of Maxwell model. Okay, now why you perturb Brownian field a little bit more to get to make it have final energy solutions? So we add some lower order terms, and we found that yes, now we can have final energy solutions which are non-trivial. Okay, and probably I should not talk too much about these models. I should stop here, and thank you very much.
Any questions?